So here we're told we have a closed piston cylinder device. It contains air. We're given the temperature at state 1 and the specific volume at state 1. And the air undergoes a power cycle composed of 4 processes, and the data at each state is given in the table below. So we have these 4 processes. 1 to 2 is isothermal compression, 2 to 3 is heat transfer at constant volume, 3 to 4 is isothermal expansion, 4 to 1 is heat transfer at constant volume. And again, we're given all the properties here at each of the states. We're asked to show the cycle on a PV diagram. We're asked to calculate the specific work and specific heat transfer. So those are the work and heat transfer per unit mass. And then the thermal efficiency of the cycle. So let's go ahead and get started. So we're told it's a piston cylinder device, so let's sketch that out. And we're told we're dealing with air. So the air is our system. So we'll draw a bounding dashed line around it to indicate it's our system, and we have some heat transfer into and some work being done by it. Then let's go ahead and get started. Since it's a closed system, there's no change in mass. We're going to treat the air as an ideal gas, so assume air is an ideal gas. We're also going to assume that since the air is in this piston here, the process is in quasi-equilibrium, and we'll neglect changes in kinetic and potential energy in these various processes because they'll occur. We're going to assume that they occur slowly and such. So, okay, let's go ahead and first of all, we're not, now that I'm looking at this, we're not given the pressures in these tables. We're given the temperature and specific volumes, but not the pressure. So we can find the pressure through the ideal gas law. So the pressure is just the gas constant for air times the temperature divided by the specific volume. So that's the ideal gas law that we're going to use to find the pressures. Actually, let me move that off to the side. Give me some room. We need to get the gas constant for air. So the way we get the gas constant for air, that's what that one is too, it's going to be the universal gas constant divided by the molecular weight of air. So this would be 8.314, I believe it is, from memory, kilojoules per kilomole Kelvin. Molecular weight of air we're given is right here, 28.97 kilograms per kilomole. And when you work that out, you should get 0.287 kilojoules per kilogram Kelvin. Okay, I remember that from memory, but this is the calculation for how you get it. So we have the temperature and the specific volumes for each state given here, so we can find the pressure. So I'm just going to put pressure here, and I'll put it in terms of kilopascals absolute. So when you do that for P1, it comes out to be 43.0 kilopascals. Well, I don't need to put the kilopascals, but 43.0. State 2 comes out to be 430. State 3, it's 2150, and state 4 comes out to be 215. So now that we have the pressures and the specific volumes, we can go ahead and draw our PV diagram. So let's go ahead and sketch that out. So here's P, and that'll be in kilopascals absolute. Here's our V, so that's specific volume, so that'll be in cubic meters per kilogram. And then we're told process 1 to 2 is isothermal compression from V1 to V2. So let's see, so V1 was 2, and the pressure there was 43. Just looking at our table up here, I'm looking at state 1 here. So there's our state 1, and it's isothermal compression. So an isotherm on a PV diagram looks something like this. So it's a curved line. We're going from 1 to 2, and it's compression, so that means since it's compression, I'm going from right to left on this plot. So I'll do it there. And then here's state 2. So state 2, again, looking back up at the table up here, the pressure is 430 pascals, and the specific volume for state 2 was 0.2. So there's our state 2. And the temperature for that process, T1 equals T2, is 300 Kelvin. So that's along an isotherm. Now going from 2 to 3, we're told there's some heat transfer at constant volume until T3 is 1500 Kelvin. So it's constant volume, so that means we're moving vertically. It's a higher isotherm for T3, so we're going to be moving up. The isotherm will be kind of somewhere up here. And I can look at my table here for state 3. You can see the pressure goes up quite a bit. So let me just draw state 3 here. So this is 2150 for state 3. That's along a different isotherm. And I'll take care of that in a moment. But there's my process from 2 to 3. It's again at the same specific volume. From 3 to 4, it's isothermal expansion until V4 is back to 2 meters cubed per kilogram. So that's going to put me somewhere along here. And again, we're moving along an isotherm from 3 to 4, so that'll look something like that. And let me, you know what, I'm going to draw it a little bit steeper so I don't get the pressures mixed up. Let me draw it a little bit like that. So here's state 4. Again, this is an isotherm, so T3 is equal to T4. It's equal to 1500 Kelvin. And the pressure at state 4, looking up at the table, is 215 kilopascals. And again, we're at the same specific volume as state 1. That's 2 cubic meters per kilogram. And then for process 4 to 1, we're told it's constant volume back to state 1, so that'll be straight down like that. So that's our cycle on a PV diagram. And we've got our lines of, we've got our isotherms, so that's an isotherm. Here's another isotherm. We've identified the pressure at each of the states. We've got our numerical values. We've identified the specific volumes at each of the states. And we've got our arrows on our paths. One thing to just notice is that we're moving clockwise in this PV plot, so that means we're producing work over the cycle. So this is a power cycle. And the net amount of work will just be the area inside that cycle. Okay, so anyway, we've done part A. Part B is to calculate the specific work and specific heat transfer for each of the 4 processes. So to define the work in this system is going to be boundary work or PDV work, and the specific work is going to be just the work per unit mass. So that can be written as PD specific volume V, so that's a little v, as we go from, I'm going to leave it off for the moment, but we'll integrate it from some initial specific volume to some final specific volume. So that's a specific volume, not an actual volume. It's because I want specific work, which is work per unit mass. If I wanted work, then this would be a regular volume. You can imagine if I take the mass here and I multiply it by the specific volume, like bring it over to this side, that would make it a regular volume. So that's how we're going to find the specific work. To find the specific heat transfer, I'm going to make use of the first law, which looks like this. So this is the specific total energy, specific heat transfer, specific work. And I'm going to assume, so this, if we expand out the specific total energy, that's the change in specific internal energy, plus specific kinetic energy, plus specific potential energy. And I'm going to assume that these are negligible, which I talked about earlier. So then when I simplify this, the Q into is going to be delta specific internal energy plus W by. So that's how I'm going to find each of these. So let me start with this, the specific work for each of these. So let's start with, as we go from 1 to 2. So let me write that down here, W by 1 to 2. So we're going to go from specific volume 1 to specific volume 2, PdV. Now to figure out how the pressure varies along this path, we know we're dealing with an ideal gas, right? And it's isothermal. Remember that the temperature is a constant. So from the ideal gas law, let me write this down over here. Since it's a isothermal process, this is just going to be a constant. right? This is a constant. And I could evaluate what that constant is because I know the temperature at state 1 and I know the gas constant, so I can evaluate that. But this will end up looking like the following. Right, so all I did was rearrange. Maybe I should show that as an intermediate step. I just wrote the pressure is RT over specific volume, and then I substituted this pressure in. Let me highlight it. I substituted this expression in right there. And then RT is a constant, so it comes outside the integral, and this just becomes RT. I'll put a 1 here since it's going from 1 to 2. It's the same temperature at 1 as it is at 2. This will be a natural log V2 over V1. So that's how we find the specific work from 1 to 2. And then let me do from 2 to 3. If you go back up here, you'll see the specific volume from 2 to 3 remains constant. So this is just going to end up being 0 because V3 is equal to V2. So that one's easy. And then let's do 3 to 4. Again, from 3 to 4, it's just like going from 1 to 2. If you go back up, you'll see that this is an isotherm, so the temperature is a constant there. So we'll get the same kind of expression as this. Right? So this will just be, it'll look much the same. So there it is from 3 to 4, and then finally from 4 to 1. If you go back up and look at that, that's a constant volume process, so there'll be 0 boundary work for that one. So that's that. And of course we have enough information in our tables to evaluate these numerically. So let me just give you those values. So from 1 to 2, when you plug in the numbers for that, let's say it comes out to be minus 198 kilojoules per kilogram. And then when you plug in the numbers from 3 to 4, it comes out to be 991 kilojoules per kilogram when you plug in the numbers. Okay, so that takes care of all the specific works. Now let's go ahead and evaluate the heat transfers. So let's do from 1 to 2. From 1 to 2, we already have the specific work, so we know that value. We need to figure out the change in the internal energy from 1 to 2. Now keep in mind we're dealing with an ideal gas, right? So for an ideal gas, the way we find the specific internal energy is it's just a function of temperature, right? Well, since T1 and T2 are the same, that means U1 and U2 are going to be the same. So the delta 1, 2 will just be 0. So Q into 1, 2 is going to be the specific work 1, 2, which means it's going to be minus 198 kilojoules per kilogram. Okay, so let's box that one in. Now let's go ahead and do Q into 2 to 3. The work from 2 to 3 we already said was 0 because it's constant specific volume. So this will just be U3 minus U2. So we need to look up the values for the specific internal energy at the different temperatures. So the temperature at 3, let me go back up to the table, was 1500 Kelvin. And the temperature at 2, I should have looked at that before, is 300 Kelvin. So what we're going to do is we're going to use the ideal gas property table to find those values. I'm not going to show the table here, but we can go ahead and look up those values on the table. And let me see or actually it's actually given up here in this table. I don't even have to look them up. They're given right here. So from 2 to 3, we've got, specific internal energy at 2 is 214, and for 3 it's 1205. So let's write those down. These are kilojoules per kilogram. So those just come straight from the table. So then we can calculate Q into 2,3. And then when you plug in those numbers, that comes out to be 991 kilojoules per kilogram for that one. Now let's do 3 to 4. And we have the specific work from 3 to 4, that was the 999 kilojoules per kilogram. Just let me double check that I actually computed that correctly. It's not 999, I'm sorry, this number should have been 991. Okay, so anyway, so let me fix that. Apologize for that. Okay, so anyway, for the same argument and going for 1 to 2, since here T3 and T4 are the same, that means that U3 and U4 will be the same, so this will be 0. So Q into 3,4 will be 991 kilojoules per kilogram. And then we do the final one from 4 to 1. We know the work, specific work from 4 to 1 is 0 because its specific volume is a constant. So this will be U1 minus U4. And from the table, we know that U1 will be given right up here. U1 is the 214 and U4 is the 1205. And just to communicate where it comes from, I'll just write from the table. Really, it's coming from the ideal gas table for air. But we can plug those in, and we'll get that this comes out to be a minus 991 kilojoules per kilogram. So now we have all of our specific heats and specific works. So let's go ahead and check that off. We've done all that. The last part of the problem is to determine the thermal efficiency of this power cycle. So it is a power cycle because we're generating a net amount of work. So to find the thermal efficiency, keep in mind that the way we do that is we're trying to get as much, the way we define thermal efficiency is the total work that we get out of the process. So by, let's put net over the whole cycle. It's the total amount of work we get out over the whole cycle divided by the amount of heat we put into the cycle. Now this is not the net amount of heat, it's just the heat that we're putting in. And since we're dealing with specific quantities, let me just write it like this. We're dividing the top and bottom by mass, so that this is again by net. It's like a lot of subscripts here. We can write this as the specific work over the specific heat transfer. So the net amount of work over the whole cycle would be just adding all the works up. So let me just write it all out here. Okay, so we have all of those. And then the heat transfer that goes in, now this again is not the net heat transfer, it's just the ones going in. When I look back here from 1 to 2, that's a negative, so we don't count that. That's going out of our system. 2 to 3, that's positive, so we want to put that one in there. 3 to 4, that one's positive, so we want to put that one in there. And then 4 to 1, that one's negative, so we don't want to count that. Remember, this is just into the cycle. The work is the net, so that's why we include all of the work terms, whether they're positive or negative. But for the heat transfer, it's just the heat that's going in. The picture to keep in mind is this. Here's our hot reservoir. Here's a system that we're dealing with. That's our piston cylinder system. And here's our cold reservoir. And this is the work that we're generating. Here's our QH and our QC. The system here again is what we're interested in. This is the piston cylinder with the air. But when we define our thermal efficiency, it's going to be this work here, the net amount of work we get out of our system over that whole cycle, divided by the heat that we're putting into it. It's the QH coming in over the whole cycle. We don't count the QC. The negative values here, those are the QC terms. We don't care about those. It's the QH we care about. So it's just the positives. Okay, so anyway, we can plug in the numbers here. And I think this numerator comes out to be 793 kilojoules per kilogram. And I think the denominator is 1982 kilojoules per kilogram. So when you plug these in, it comes out to be 0.400. But since we were asked specifically to write it as a percentage, I'll just write it as 40%. So that's our thermal efficiency for this power cycle. Okay, so let me just make sure we covered everything. Yeah, that was part C. So we'll check that off. So we did everything we've been asked to do. If I recall correctly, this was a former ME 200 exam problem. So you can see what a typical exam problem might be like. Okay, I think we covered everything. You know, it's a matter of drawing a PV diagram, applying, calculating boundary work, applying the first law, being able to do some integrals here, knowing that with an isothermal process, with an ideal gas law, we get that kind of expression. So we're assuming an ideal gas along the way. This is another important thing, is just knowing that for an ideal gas, specific internal energy is a function only of temperature. And then the last bit is calculating the thermal efficiency, knowing how that's defined. And probably the thing that confuses most people is just making sure that they get the right Q. It's the QH here, that the stuff that's coming into the cycle, and making sure those are correct. Okay, well.